Section. Introduction. We're going to talk about the challenges and potential solutions in the field of large language models. These models are becoming increasingly proficient at a range of tasks, but as they improve, it's becoming more difficult for humans to supervise them effectively. This is because as the models become more complex, they require more expertise to manage and monitor. One issue we've noticed is that AI assistants often agree with user misconceptions instead of providing accurate information. This is likely due to the AI's heavy reliance on human feedback. As we move towards models that outperform human experts, we'll need to develop new ways to supervise them. One proposed solution is to enhance human graders with AI assistants. These assistants would be trained using feedback from humans, creating a recursive learning process. This method has shown promise in early experiments. Another potential solution is to train superhuman ICE to compete in debates judged by humans. In this paper, we're going to expand on the eliciting latent knowledge (ELK) approach. ELK aims to find patterns in an AI's behavior that consistently point to the truth, even when the AI's output is misleading or false. These patterns can be translated into understandable information by a classifier, or probe, which is trained on data extracted from the base network. Alternatively, we can use anomaly detection methods to flag when the network's output may not be trustworthy. The challenge with ELK is finding patterns that can be applied to questions we can't verify. Essentially, ELK is trying to solve the problem of information asymmetry between a superhuman AI and the humans evaluating its behavior. By eliminating this asymmetry, ELK might be able to address the potential failure modes where an AI deceives humans by pretending to be aligned during training, but then acts destructively during deployment. We believe that an ELK method can be useful even if it's not more robust than other sources of information, as long as its errors are not correlated with the errors of existing methods. In this paper, we're going to present our findings from a new experimental setup for benchmarking probing and anomaly detection approaches to ELK. We'll also be releasing our models and datasets. We found that probes fit with both supervised and unsupervised loss functions generalize well from easy examples to hard examples, and from truthful examples to untruthful examples. We also found that off-the-shelf anomaly detection algorithms can accurately detect when the model isn't tracking the truth, without needing any labeled examples of untruthful behavior. For an ELK method to be useful, it needs to provide reliable answers even when neither human experts nor language model outputs can be trusted. This means that supervised ELK methods need to be robust to two key shifts in distribution, from easy to hard, and from truthful to untruthful. In this paper, we use a method called parameter-efficient fine-tuning to create Quirky models that are truthful in some contexts and untruthful in others. This allows us to test how well the models generalize from truthful to untruthful. We designed our fine-tuning dataset to meet certain criteria. Each prompt is a statement with a binary true-false label. We believe that probing for the truth value of a statement is enough to elicit latent knowledge in most real-world scenarios. The untruthful answers should not simply negate or inject randomness into the truthful answers. The two distributions should be systematically different in a non-trivial way. Our dataset, Quirky Math, consists of addition equations followed by a Boolean label generated by one of two personas, Alice and Bob. Alice is perfect at addition, while Bob always believes the sum should have a first digit 1 greater than the true sum. We experimented with 3 prompt template setups: persona first, persona last, and mixture. The mixture template setup also incorporates data augmentations during fine-tuning and is intended to induce the desired mechanisms at a higher level of abstraction. We also defined easy and hard splits of the dataset to test the ability of current methods to generalize to hard examples when trained only using easy examples. An easy example is one in which the shorter of the two summons is 2 digits or shorter. A hard example has a shorter summand of at least 4 digits. The models we used in this paper on average achieve 97% OROC on Alice's easy subset and 89% OROC on Alice's hard subset. Section Summary. Large language models have shown impressive performance on various tasks but require increasing investments in subject matter experts for supervision. To address this, the paper proposes amplifying human graders with AI assistants, trained recursively using feedback from humans. The paper extends the eliciting latent knowledge (ELK) approach, which aims to locate patterns in an AI's activations that point to the truth, even when the AI's output is misleading. The authors construct a benchmarking setup for ELK methods and demonstrate the effectiveness of probes and anomaly detection algorithms in detecting untruthful behavior. Section: Fine-tuning. We're refining our models to predict how characters like Alice or Bob would interpret each equation based on the context. We make minor adjustments to the model's parameters using a rank-8 LoRa method on all attention and MLP modules. We fine-tune several models, including Pythia, LLAM-A2, and Mistral, using different templatization methods, resulting in 24 unique models that we study and release. We've confirmed both empirically and qualitatively that the language model's behavior on pre-training text remains unchanged, as detailed in the appendix. We're experimenting with 6 probing methods, as well as a random baseline. All methods are linear, 4 are supervised, and all probes take the residual stream activations from a single layer and output a score. We train a probe on each layer. One method we use is linear discriminant analysis, LDA, a classification method that depends only on the mean and covariance of the data for each class. It assumes that each class is distributed as a Gaussian and that all classes share the same covariance matrix. For 2 classes, the LDA weight vector is proportional to the difference between the class conditional means, divided by the shared covariance matrix. We also use a simplified version of LDA, called difference in means, which assumes that the shared covariance matrix is a multiple of the identity matrix. In this case, the weight vector is simply proportional to the difference in class conditional means. This method has been found to better support causal interventions on language model activations and is more robust to distribution shifts. We also experiment with logistic regression, using a fixed L2 penalty of 0.001. We use 2 unsupervised methods that work with contrast pairs of input examples that differ only by negation. These methods are not directly comparable to supervised methods because they see different activations. We discuss the limitations of these methods in a later section. One of these methods is contrast consistent search, CCS, which searches for a linear probe that is consistent with negation, meaning its predicted probabilities for a statement and its negation approximately sum to 1. The other method is contrastive representation clustering, CRC, which uses the top principal component of the vector differences between representations of statements and their negations. We also experiment with logistic regression on contrast pairs, where the input to logistic regression is constructed by concatenating the activations of the contrast pair. Both unsupervised methods locate a one-dimensional linear subspace but have an issue with sign ambiguity, which is resolved by negating the probe's weights if the resulting probe achieves less than 50% OROC on a labeled validation set. We perform 5 main transfer experiments, using 4,096 examples for training and 1,024 examples for evaluation. These experiments involve transferring probes trained on one set of examples to another set to evaluate their generalization behavior. For example, we train a linear probe on the model's activations to predict whether Alice would label the example as true or false, and then apply these probes on activations produced for examples containing Bob. We also look at truthfulness generalization in the reverse direction to see if pre-training has induced any asymmetries in how knowledge is represented. We transfer probes trained on Alice's easy examples to Alice's hard examples to understand the limitations of only having access to easy examples for training. The key transfer experiment for evaluating ELK measures whether probes trained only on trusted easy examples can provide useful information in contexts where the model is untruthful on hard math problems. A central motivation for the unsupervised methods is to remove the need to rely on imperfect labels to probe for superhuman knowledge from capable models. We include transfer experiments where we learn CCS and CRC probes on all examples and evaluate them on Bob's hard examples, as a practical comparison to learning a supervised probe on Alice's easy examples only. In this setting, we use an oracle, Alice's labels, to resolve the sign ambiguity. Section summary. In this section, the authors describe their approach to fine-tuning models to predict how Alice or Bob would evaluate equations based on context. They experiment with various probing methods, including linear discriminant analysis, logistic regression, and contrast pairs. They also perform transfer experiments to evaluate the generalization behavior of the probes in different scenarios. Section: Selecting a layer. We need to choose a specific layer from our model to examine, and this choice is crucial. We've found that the middle layers tend to be more versatile than the later ones, while the early layers don't provide much useful information. So, we suggest using the earliest informative layer criterion, which means we select the earliest layer that provides useful information. We define this by comparing the in-distribution area under the receiver operating characteristic, AUROC, for a probe on a specific layer to the maximum AUROC over all layers. If no layer provides useful information, we default to the middle layer. We then use a method called mechanistic anomaly detection. We create an anomaly detector without any examples of anomalies, using simple examples as a reference. We create a feature vector for each example by combining the probe outputs from all the layers. We then fit a Gaussian distribution to these feature vectors and use the Mahalanobis distance as the classifier score. This distance measures how different an example is from the reference distribution. We evaluate this by comparing difficult examples from two different sources. Both of these sources are different from the reference distribution, which makes it more challenging to identify the difficult examples. Before we started our experiments, we had three hypotheses about how language models represent knowledge. The first is context-dependent knowledge, where each persona's knowledge is only represented when the persona is present. This would make it difficult to extract truthful answers from the model's activations when it is behaving untruthfully. The second is context-independent knowledge, where each persona's knowledge representation is present and can be read in all contexts. This would make it easier to extract truthful knowledge even when an untruthful persona is influencing the model's output. The third is the chameleon hypothesis, where only the representation of truth exists across all contexts, and the output is a modification of this central representation to fit the context. Our results show strong evidence for the existence of context-independent representation of knowledge. Probes trained on one source agree with probes trained on another for a large fraction of the examples where both sources label the statement as false. This indicates that the two sources are not simply opposites of each other. We also find some context-dependent knowledge representations, particularly when probing later layers with supervised methods. This makes sense since the residual stream in later layers is more directly involved in the language model output. We also found that probes generalize well from easy to hard examples. All 6 probing methods are useful because they consistently report the model's latent knowledge of the truth even in contexts where the model's output is untrustworthy and the problems are harder than any used for supervision. However, both unsupervised methods perform significantly worse when making use of all data for training, which negates their usefulness. In conclusion, our results show that simple anomaly detectors fit on probe outputs from easy examples can distinguish hard examples from two different sources well across models and probing methods. This gives practitioners more confidence that their probe will robustly point to knowledge that is not correlated with the model output.